In the previous video, we introduced two ways to measure performance. In this video, we're going to continue where we left off, but we'll shift the dialog to compiler optimizations. Compiler optimization modes change the way Xcode's LLVM compiler compiles your code. By default, it compiles each code file individually, allowing the compilation of your code to take place on multiple cores. This, of course, makes for faster build times during development. In this default mode, when you rebuild your application after making some changes, Xcode only recompiles the code that needs to be updated, making for much quicker builds. The problem is that the compiler's optimizations are limited to the scope of one file at a time. Xcode 7 introduces a new optimization mode named Whole Module Optimization, which, as the name implies, optimizes the entire module at once. This provides a tremendous performance boost as the compiler can analyze the whole module and make aggressive optimizations to the generated binaries. The trade-off, of course, is that the whole module optimization build takes longer because you're recompiling the entire module each time. For an in-depth discussion on compiler optimizations, I would recommend watching WWDC 2015 Session 409 titled Optimizing Swift Performance. I'll provide a link on this video's resource page here. Let's look at whole module optimization in action. In our last video, we were getting very similar speeds between our custom filter operation and Swift's filter operation. This is a bit odd considering that our custom filter is built quite a bit lighter than Swift's. Our filter leans on the array type rather than conforming to sequence type and rolling our own generator like Swift's filter does. Swift's filter also has the added functionality of being able to throw and rethrow errors. Let's change the mode of operation to see if it garnishes any different results. Click on the root project and select Build Settings. Once there, type Optimizations in the search field to filter our options down. We'll take our debug and switch it to Whole Module Optimization mode. Now let's rerun our tests starting with Swift's filter type. Open life.swift and make sure we're using Swift's filter. Then open your test suite and perform the measurement. As expected, Whole Module Optimization mode is quite a bit faster. Let's test our version of filter to see if there's been an improvement. Open life.swift and switch Swift's filter for our custom filter. Now let's go back and rerun our tests. Okay, this time we're running measurably faster. Let's run our application and see if it's noticeably faster with Whole Module Optimization. Once your application is loaded, run your game. This is notably faster. Let's look at it side by side. The left side of the screen is with optimization, and the right side of the screen is with no optimization. Let's switch Whole Module Optimization off and run Time Profiler on our game and see how it performs. Let's build and run and transfer our session to Time Profiler, and then we'll run our game. Now that we have some measurements, let's see how our application performed. Before we switch to Whole Module Optimization, let's see how much CPU our custom filter function uses. We'll have to expand a few nodes and here it is. Let's switch from no optimization to Whole Module Optimization and build our application. Now let's transfer our session to Time Profiler and run our application again. And we see we're using a fraction of the CPU power that we were without Whole Module Optimization. Again, let's see how our custom filter fared. This is interesting. Our custom filter function is nowhere to be seen. This is because the Swift compiler is actually inlining our Swift function, which is another reason why our custom filter runs faster than Swift's native filter in Whole Module Optimization mode. An inline function is a function that is stored and called directly from an address, which is also known as a call instruction. Ordinary functions use this call instruction to transfer control to the function's definition. Avoiding this definition lookup can often speed up our function's call. For more information on inline functions, see this video's resource page. Let's see what happens when we tell Swift not to inline our function. Open utility.swift and add the following line above our custom filter function. This will tell the compiler never to inline this function call. Now let's build and run our application and transfer it to Time Profiler once again, and then run the game. Let's drill down the main thread stack and look to see if our custom filter function exists. And there it is. In this video, we've effectively used Time Profiler and XCTest to track down why our filter function was performing better than Swift's in whole module optimization mode. In the next video, we'll see how we can improve the performance of our code even further by reducing dynamic dispatch.